Suppose we want to estimate the number of candies we would expect in a standard bag of Yums, a made-up name. I very cleverly made up that. That is, we want to estimate mu, the population mean number of candies per bag. We are given that sigma equals 3, and I'll point out that that is unrealistic that we know what sigma would be, not just because it's a made-up candy, but because to know the population standard deviation, that implies that you would know the population mean, but just to develop the theory, we're going to assume that we know sigma. So just bear with me on that. All right, so how would you estimate mu? Or how would you determine how many Yums to expect in a bag? Well, this goes back to a previous discussion of you would buy a bag of Yums and count how many candies are in that bag. But the issue is only buying one bag and taking that number in that bag has a lot of variation in it. So what we would do is apply what we've done the last couple of chapters. We would take a sample of size n, calculate x bar, the sample mean, and then apply the central limit theorem with the sampling distribution of sample means. All right, so suppose we take a sample of 36 bags of Yums and calculate a sample mean to be 87.2 candies. So I bought 36 bags, counted the number in each bag, and the mean of those 36 bags is 87.2 candies. So some may have had 85 candies, some may have had 90 candies, some may have 87 candies, but the average of that sample of 36 bags is 87.2 candies. So after taking our sample of 36 bags, what is our best guess or best estimate for mu? Remember, mu is the population mean number of candies in all bags. So if someone were to ask you, well, I'm thinking of buying a bag of Yums, how many candies would I expect? What would you tell them? Well, you would tell them your sample mean, 87.2. That's what you would expect. Okay, so our best estimate or best guess for mu is x bar equals 87.2. So x bar, our sample mean, is our best estimate for mu, the population mean. Okay, remember that we only collected one sample of size 36. Another sample of 36 may result in a different sample mean. The theory is that we can repeatedly collect samples of 36, resulting in the SDSM. Therefore, we apply the theory of the SDSM and the central limit theorem. So what is the value of sigma sub x bar? Well, remember that sigma sub x bar is sigma over the square root of n. They told us that sigma was 3 divided by the square root of n, so the square root of our sample size 36. So that's 3 over 6 or 0.5. Okay, so the standard deviation of our sampling distribution, of our x bar distribution, is 0.5. So using our best guess for mu, which was 87.2, and the value of sigma sub x bar, which is 0.5, we're going to calculate each of the following. So x bar plus or minus sigma sub x bar, and then we're going to add and subtract 2 sigma sub x bar from that sample mean, and then add and subtract 3 sigma sub x bar from that sample mean. So what this is basically asking us is calculate the values that are 1 standard deviation from that sample mean, 2 standard deviations from that sample mean, and then calculate the values that are 3 standard deviations from that sample mean. And remember, the idea here is that sample mean is our best guess for mu, 87.2. Okay, so I'm going to uncover the answers here. You should be able to do this. So I'm going to uncover the answers. And pause the video if you need to. Okay, so our sample mean 87.2 plus or minus our standard deviation of the sample mean, which was 0.5, gives us an interval of values from 86.7 to 87.7. Now this may look a little different than what you've seen before, but what you basically do, you get two different answers here because of the plus or minus. So you take that sample mean, add and subtract sigma sub x bar, you put the smallest number first, 86.7, and the larger number second, 87.7. These parentheses just represent what we call interval notation, which means all the values between 86.7 and 87.7 are within one standard deviation of the mean. So if you were to think about these on an axis, and I'm not going to do this for every single one, but if you were to look at these on an axis, you would have 87.2 in the middle, which is what we think, which is our best guess for the population mean, 87.2. And we would go 0.5 above and below that to get 86.7 and 87.7. Okay, so all the data values between 86.7 and 87.7 would be within one standard deviation of the mean. Same idea, if you go two standard deviations from the mean, now we're just going to add 0.5 twice. So there you get an interval 86.2 to 88.2. So what that would be doing on an axis, again, you have 87.2 in the center, which is our best guess for the population mean. And going one above the mean would give us 87.7, and then two above the mean would give us 88.2, and then one below the mean was 86.7, two below the mean would be 86.2. Okay, so what this is basically saying is any data, the data values between 86.2 and 88.2 are within two standard deviations of the mean. Okay, and then a similar case for the 3. Okay, and what you should notice is that as you multiply the standard deviation here by 1, 2, and 3, notice your interval gets wider. Basically just saying you're going out farther and farther to the ends. The more standard deviations that you add, or that you go from the center, the wider your interval is going to be. Okay, so by the empirical rule, what is this telling us? Well, the empirical rule was an earlier section in our book. Approximately 68% of the data lie within one standard deviation of the mean. So what we just did implies that approximately 68% of the data lies between 86.7 and 87.7. Approximately 95% of the data lies within two standard deviations of the mean. So with our second interval that we formed, we're saying that approximately 95% of the data lie between 86.2 and 88.2. And then the empirical rule says 99.7% of the data lie within three standard deviations of the mean, or between 85.7 and 88.7. Okay, so now let's suppose we took another sample of size 36, and this time we get a sample mean of 88. So the first sample mean we got was 87.2. We take another sample of size 36, and just suppose we get 88 for that sample mean. Now, using our best guess for mu and the value of sigma sub x bar, calculate the following. Well, based on this sample, our best guess for mu is going to be 88. So we're going to take 88 plus or minus the standard deviation. Now, what's nice about this is as long as our sample size stayed the same, 36, our standard deviation of x bar is not going to change. That is still 0.5. Okay, so these calculations are similar to the last page. Okay, except now instead of starting at 87.2, you're starting at our best guess for mu of 88. But notice that the error here, the 0.5, 2 times 0.5 or 1, and 3 times 0.5 or 1.5, those numbers stay the same. So the width of our interval stays the same, and this is important. The width of the interval stays the same, except the middle of our interval was now 88. And here, when you go 1 standard deviation above the mean, now you're at 88.5. And one standard deviation below the mean, you're at 87.5. Okay, so the width of our interval stays the same, except our interval has shifted a little bit to the right, because now instead of the middle being at 87.2, now it's up at 88. And I try not to belabor that point, but that is kind of the point of confidence intervals, is that the idea is we're going to take samples of size n, in this case 36, and your estimate for mu for the population mean is potentially going to change based on what you get for the sample mean. And any sample you take could have a different sample mean. Okay, and that's kind of the big concept here. Okay, so I just give you one of the cases here. Looking at 2 standard deviations from the mean, 95% of the data lie between 87 and 89. Okay, so that's the second one here. Okay, so how do we interpret this? If we were to take one sample of size n, so in our case we took 36, we say that we are 95% confident that our interval x minus 2 sigmas of x bar, comma, x bar plus 2 sigmas of x bar, which is just what this is here. Okay, so I know it looks confusing with all the symbols, but that's all that we did right here. We are 95% confident that our interval will contain the true value of the population mean mu. So we are 95% confident that our interval, 87 to 89, contains the true value of mu. Now sometimes that doesn't make a lot of sense exactly what that is telling us. So I always think a better way to look at this is the next part here. So for a 95% confidence interval, if we repeated this process 100 times, meaning take 100 samples of size n and construct an interval for each sample mean, we did 2 of them already with 87.2 and 88 as our sample means. So if we did that 100 times and constructed an interval around each sample mean, we'd expect 95 of those intervals to contain the true value of the population mean. So there's an applet online that I'm going to show you some of the results. Okay, if you go to Google and you Google search confidence interval applet W.H. Freeman, it should come up pretty quickly. And what I'm showing you here, if we take one sample of size 36, remember the concept is we have a sampling distribution of sample means and we have the original distribution. The wider distribution is the original. So over here, this distribution here is the original distribution, and then the taller, skinnier one or more narrow one is the SDSM, the sampling distribution. Okay, now, it sounds kind of weird, but remember that we do not know what mu is. But by the central limit theorem and what we know about sampling distributions of sample means, we know that the mean of the original population is going to be the same as the mean of the SDSM. And we know that that's going to be right in the center of our normal curves. And I should mention we took a sample of size 36. So we know that this tall skinny one, the SDSM, we know that one is going to be normal because our sample size is larger than 30. Okay, so what we're doing here, if we took one sample of size 36, we get these 36 dots down here. Okay, so each of these dots represents the number of candies in the bag. And we calculate the sample mean, and that's what this dot is right here. So if you were to average all these together, all these numbers together, you get this dot. Now notice that dot is just to the left of where mu is. Now again, we don't know what number mu is yet. That's what we're trying to estimate. Okay, but also notice how there's like tails coming off to the left and to the right of the sample mean. That represents your confidence interval. Okay, so the end of this and the top of this are the endpoints of your confidence interval. So in the first example, we had 87.2 as a sample mean, plus or minus 0.5, and then 87.2 plus or minus 2 times 0.5. Well, the 95% confidence interval, we said that was about 2 standard deviations from the mean. So that would represent this one here. Okay, so what this little diagram is telling us is that this left endpoint could, now again, I'm just giving an example that this was 87.2 for the sample mean. So if that was it, then 86.2 would be the left endpoint and 88.2 would be the right endpoint. So this value would be 86.2 and this endpoint would be 88.2. If it happened that that was the sample for the other one, where 88 was the sample mean, then with 2 standard deviations from the mean, because we're 95% interval, 87 and 89 are the endpoints. So this could have been 88 right here in the center for the sample mean, and then this could be 87 here and 89 over here. Again, we don't know exactly which one it is because we don't know what the numbers are on the axes, but I'm just giving you an example using the one that we did. Okay, so the theory here is if we take 15 samples of size 36, every time you take a sample of size 36, you create a confidence interval around that sample mean. So here's one of them. Now notice that mu is just at the end of that interval. So that interval actually contained mu. The next one, same thing. The next one, same thing. The next one, the sample mean was a little above mu, but the interval from the left endpoint to the right endpoint, notice that where mu is, right here, right down the middle here, notice that that is still within that interval. And what you might notice is all the way until you get to this one. Okay, this one is the first time that you miss mu. And that's what the theory here is. If we repeated the process 100 times, we'd expect 95 of our intervals to contain the true value of the population mean. So this here, this interval, is the first one that missed. We went 1, 2, 3, 4, 5, 6, 7, 8, 9 before we missed one on the 10th. So if we had 100 of these, we would expect 5 of them to miss the value of mu in the middle.